Hi, welcome back to my YouTube channel. Today we are going to look at radioactivity. What is radioactivity? Radioactivity is the spontaneous disintegration or decay of the nucleus of an atom of an element, during which it emits alpha particles, beta particles, or gamma ray, or a combination of any or all the three and energy. Now let us look at the board so we can explain this concept of radioactivity. The spontaneous disintegration or decay means that certain elements on their own, they emit radiation naturally, and when they emit this radiation from their nucleus, they can emit either alpha particles or beta particles or even gamma ray. Some can even combine two radiations, like emitting both alpha and beta together, and once that is done, a new element is formed, and that new element that is formed will have a new mass number and atomic number. Watch this video to the end so I can explain to you how this element emits radiation and how this new element is being formed. The three types of radiation we are talking about: one is alpha. Alpha particle is a helium nuclide. A helium nuclide which has a mass number of 4 and atomic number of what? 2. Beta particle is an electron. This has mass number of 0, atomic number of what? -1. Gamma ray is this. It has mass number of 0, atomic number of what? 0. Any element that can emit such radiation, they are said to be radioactive what? Elements. They are said to be radioactive elements because radioactive elements emit radiation spontaneously from their nucleus. That means they emit the radiation naturally from the nucleus. And examples of such radioactive elements are what? Uranium, polonium, radon, thorium, and so on and so forth. There are several theories on radioactivity, but there is this man that first discovered this phenomenon in the year 1896 by the name Henry Becquerel. While he was performing an experiment with a radium sample with his co-workers, he now realized and observed that we have three types of radiation. Some radiation was going towards the north, while some was going towards the south, and a particular radiation shows no deflection. He now concluded that we have three types of radiation obtained or observed from a radium sample. Let's look at what we have on the board. This is a radium sample. Then this lead block is used to shield this radium sample so that the radiation cannot escape. So when this radium sample is incident on a photographic plate, it shows three types of radiation. This radiation was moving towards the south pole of a magnetic field. This was moving towards the south, while this was moving towards what? The north. Now the one that was moving towards the south is said to be alpha particles. Why is it said to be alpha particles? Because south pole are meant to be negatively what? Charged. So for attraction to take place, the positive must attract towards the negative. That is why this is what? Alpha particles. Now coming to this one shows a much deflection, and it is being attracted to the north pole of a magnetic field. The north pole is meant to be positively what? Charged. So for attraction to take place, negative must attract what? Positive. So this is beta particles. Look at this middle one. This one shows no deflection, so it is said to be what? Gamma ray. From the conclusion of this deflection of particles, we have three types of radiation: the alpha particles, the beta particles, and the gamma ray. Certain radioactive elements have half-life. What is half-life? Half-life is the time taken for a radioactive element to decay to half of its original value. For example, if this element has a mass, this is original number of atoms before decays, a mass of 20 gram, and if the half-life of this element is 4 years, it means that after 4 years, this 20 gram will decay to half of its original value. That will be N0/2. When I come here, it's going to give me what? 10 divided by 20 divided by 2 is going to give me what? 10 what? Gram. Then, if this half-life continues, is it going to decay to half of its original value? That is N0 over what? Half of this, which is N0/4, which will give rise to what? 5 what? Gram. So certain element tends to decay to its original value. Please, if you have not subscribed to my channel, do well to subscribe, comment, like, and share. And please watch this video to the end so you can understand and be able to solve any problem relating radioactivity in this forthcoming NACO 2024 exam. Decay constant is defined as the instantaneous rate of decay per unit atom of a substance. The rate at which this atom decay is what we call what? Decay constant. And there is a relationship between half-life and decay constant. That relationship is what? I use T half as half-life is equals to 0.693 over lambda, and lambda is decay constant, or lambda is equals to 0.693 over half-life, where T half is equals to half-life and lambda is equals to decay constant. Let's look at decay curve and half-life. This is the original number of atoms before it starts decaying. If the half-life happens to be 4 years, like I said earlier, the atoms will decay to half of its original what? Value. And if it also increases again, another 4 years, it's going to what? Decay to half of its original value. So the first decay is N0, which is the original number of atoms before decay, divided by what? 2. And the value is here. Then the second decay is what? N0, that is half of this one, that is N0 over what? 4. You can now see that this is a decay curve. So as the time progresses, the number of atoms tend to do what? Decrease. That gives you a decay what? Curve. So as time progresses, the number of atoms decreases. I hope you understand that. Let's look at radioactivity formula. This formula is going to be used to solve most problems involved in radioactivity. We have N over N0 is equals to 1/2 bracket power of T/T half. What is N? N is number of atoms after what? Decay. N0 is number of atoms before decay. T is time, and T half is what? Half-life. We have two types of radioactivity: natural radioactivity and artificial radioactivity. This natural radioactivity is the same thing as our radioactivity, which is the spontaneous disintegration of the nucleus of an atom of an element, during which it emits alpha particles, beta particles, or gamma ray, or a combination of any of the three and energy. So we are going to see the equation that represents natural radioactivity. Artificial radioactivity is a situation whereby an ordinary element that is not even a radioactive element, it is made to start emitting radiation on its own as a radioactive element by bombarding it with particles such as neutron, protons and deuteriums. And if we bombard them, they tend to emit radiation as a radioactive element. So let's see the equation that distinguish between natural radioactivity and artificial radioactivity. This equation represents natural radioactivity and artificial radioactivity. So this is under natural radioactivity, while this is what? Artificial radioactivity. This is a radioactive element. It tends to emit radiation spontaneously from its nucleus. This is radium with mass number 226 and atomic number of 88. It tends to emit alpha particles, which has a mass number of 4, atomic number of 2, and gave rise to radium, which has a mass number of 222, atomic number of 86, plus what? Energy. This energy evolved in this process what we call the binding energy. It is the energy it takes them to bind together to form this. Now, you must note that the masses of this product is less than the mass of the reactant. Why? Because of this energy lost in the process of the formation. The second equation is under artificial radioactivity. Look at this equation. This is lithium. Lithium is an ordinary element which has a mass number of 6 with atomic number of 3. Now, we can see that we bombarded it with neutron because it cannot emit radiation spontaneously on its own. So, when we bombard it with neutron, it cannot act as a radioactive element. Going to emit hydrogen, which has a mass number of 3, atomic number of 1, with a helium, which has a mass number of 2, atomic number of 4, and the emission of what? Energy. Like I said earlier, this energy is the binding energy that this element can take for them to form this reaction. Nuclear energy. We have two types of nuclear energy. We have nuclear fission and nuclear fusion. So let's see what we have on the board. Nuclear fission is the splitting up of the nucleus of a heavy element into two approximate equal parts with the release of a huge amount of energy and neutrons. This is uranium, which is a huge amount of element, which is also a radioactive element. If it is being bombarded with neutron, it's going to emit particles like boron and krypton with neutrons and energy. Now, this energy involved is said to be our what? Binding energy. And this binding energy is giving us a change in mass c square, where this change in mass is what we call mass defect. Mass defect, which is change in the masses of the reactant and the product, because the masses of the product is always less than the masses of the reactant because of this energy that is being emitted. Okay, so c is equals to the speed of light, because the particles move with the speed of light, which is a constant and is equals to 3 times 10 raised to power 8 meters per second. The second part of the nuclear energy is nuclear fusion. The word fusion means when two light nuclei come together to form a heavy nucleus with the release of a huge amount of energy. Look at it. Hydrogen combined with another hydrogen to form what? A helium and neutron with a huge amount of what? Energy. This energy also is also called the binding what? Energy. Now you can see the difference from the equation between the nuclear fusion and nuclear fission. In nuclear fission, the element is a huge element and it splits to form two equal small elements with energy. But in nuclear fusion, we have two light nuclei combined to form a heavy nucleus with the release of a huge amount of energy. Now you should know the advantages of nuclear fusion over fission. Some of the advantages is this: the raw materials used in production of nuclear fusion are cheap and readily available compared to nuclear fission. Nuclear fusion produces less dangerous by-product. Nuclear fusion can be achieved with the lightest elements like hydrogen, unlike nuclear fission. We have some peaceful uses of nuclear energy. This can be used in radiotherapy, we have in radioisotope, we have in medicine, and we have in spacecraft. So these are the things we need to know under radioactivity. I hope you love this video. Please subscribe to my channel, share, like and comment. Stay tuned.